Hi everyone. So today in class we looked at functions, what makes something a function. And just as a reminder, I said that the best way to determine if a function, a relationship or a relation is a function is to look at the ordered pairs or the graph and see if it has there's the same x value but different y values. So I look for repeated x's. Okay? Repeated x's that have different y's. So I look at this first example, and I think we looked at this in class. I gave you the ordered pairs 5, 1, -3, 5, 8, 1, 2, 7. I look for a repeated x. I do not have any repeated x's, so that means that this is a function, okay? Whereas in B that we looked at when we found repeated x's here. So when we saw those repeated x's, we needed to check the y values. And this one has a y value of 1, this one has a y value of 3, which means they do not have a unique y for each x, so that would not be a function, okay? Now, that's if we're looking at ordered pairs. Remember, I also said that you could look at mappings, meaning you have your ovals where we're mapping numbers to numbers. Again, the inputs were the x's, the outputs were the y's. It's a little bit trickier here because if you look at this one is being mapped to 2 and to -2 and to 1. That means if I wrote that as an ordered pair, I would have 1, -2, and I'd have 1, 1. Again, it's a repeated x with a different y, so no, it is not a function. All right, let's look at this other one. My inputs here and my inputs here. I have -3 to 3, I have 1 to 1, I have 3 to 1, and I have 4 to 2. So I don't have any repeated x's. I can have repeated y's and it'd be a function, but I cannot have repeated x's. So right here could be tricky for you, but the ordered pairs would be 1, 1 and 3, 1. Again, they're not repeated x's, so it is a function. Okay. Now, one of the ways I told you could look at a function was by a graph or a relation. You could look at it by looking at a graph. Well, there is a quick way to determine if something is a function using something called the vertical line test. A relation is a function if and only if no vertical line intersects the graph of the relation at more than one point. And I think you need to fill that in, at more than one point. So basically, if a vertical line passes through 2 or more points on the graph, then the relation is not a function. I'll be looking that you wrote that in your notes. For a graph to be a function, all vertical lines must touch in only one spot or not touch at all, okay? Or not touch at all. All right, well, let's look at some examples. Now, a couple of things. These graphs kind of end. I want you to put arrows on the end here and here and here and here. That tells me that those values, that graph continues on forever. All right, so if I want to use the vertical line test and I look at this, is the vertical line, it passes the graph here once. Anywhere I draw a vertical line through it, it's only going to hit the graph once, so it passes the vertical line test, so it is a function. I look at this next one. I draw a vertical line through it. It hits in 2 places, so it is not a function. Okay? What I'd like you to do is do the next 3 on your page and bring that into class tomorrow, and we will check. And we'll talk more about that vertical line test. But today we're going to talk more about domain and range, okay? So domain and range relate to functions, and they help us identify what values we can use in the function and some other things as they relate to functions. So the domain of a relation is the set of all the inputs or the x coordinates of the ordered pairs. Okay, the domain of a relation is all the x's, whereas the range of a relation is the set of all the outputs, which means all the y coordinates of the ordered pairs. Domain and range can actually be written as an inequality or by using something called interval notation. So let me show you what I mean. All right, so we're going to look at it in words, as an inequality, and with interval notation. All right, so in words, the inequality here says x is greater than or equal to -4. So in words, that domain would be all x greater than or equal to 4. In interval notation, we would write that as a hard bracket, -4, comma, all the way to infinity, because that's where it's going. If you think about the graph, here's the number 4. If I graphed this inequality, it means that. And remember I said that on a number line, over here is -infinity and over here is infinity. So this graph is going from -4 to infinity. The hard bracket means that it includes -4. So because this was an equals inequality, I have to use a hard bracket. Now, on the opposite of infinity, I can't include infinity because infinity never ends, so I put a parentheses. Okay, let's look at the next one. X is greater than -2 and less than -4. All right, so that's where I've got x is greater than -2 and less than -4. So that's an and compound inequality. That means I want all the values between -2 and 4, but not including -2 and 4. In interval notation, we would write that as -2, 4 in parentheses. Now, if I put an equals, I'd put a hard bracket. If I had put an equals here and here, then I would change that to a hard bracket, -2, 4, because that would tell me it includes those numbers. All right, and the last one. Not sure if you've ever seen this notation before. It looks like a funny looking R. When I draw it, I write it like that. It means all real numbers. Okay, all real numbers. How do we write that? We would say in inequality, we actually wouldn't write it as an inequality. We would say all x, okay? Or x such that, okay? Interval notation, we write that as -infinity, infinity. That means all real numbers. Okay, so now I'm going to put this together and show you how you find domain and range, and how we would then write it in interval notation. So finding domain and range when it's ordered pairs is very easy. Remember, I said the domain was the x coordinates or the inputs, and the range was the y coordinates, also called the outputs. So my domain here would be 5, -3, 8, and 2. Now, typically we want to write them in order from least to greatest, so I really would probably write that as -3, 2, 5, and 8. And you could put that in parentheses. Range, you then look at the y values, and let's do it from the get-go in order. So we would do -7, 1, and 5. Now you might notice I don't have to repeat, even though I have repeated y's, I don't have to repeat it in the range. All right, let's look at the domain on this. Now, we already determined that this one wasn't a function because it had repeated x's with different y's. But a relation can have a domain and a range, okay? So my domain here would be, let's see, -2, 1, and 3. And my range would be, let's see, we've got no negatives there, so 0, 1, 3, and 4. The good news with domain and range of ordered pairs, it doesn't have to have the same number of units in the set, okay? This one has 4 in its set, and this one has 3. All right, but what about when we look at a graph? When we want to find domain and range of graphs, for the domain, if domain is my x values, that means I only want to look along the x-axis. So that means I need to scan my eyes from left to right along the graph. Left to right, so along the x-axis. So looking at that first one, along the x-axis. For the range is the y value, so I want to scan my eyes from the bottom to the top. We always go from the lowest to the greatest, right? So from the bottom to the top. Now, I'm going to label here on this first one. Now, please go ahead and put arrows at the end of the line here and again at the end of this parabola. Now, you looked at these when we talked about whether they were functions or not, but now we have to look at their domain and their range. So you have to, in your mind, imagine this line is going on forever in this direction and ever in this direction. So if you think about all the x's it's going to have an x-coordinate way, way up here. Is it going to have an x-coordinate? It will. So everything along the x-axis is going to be hit, okay? So as a domain, that would be negative infinity to infinity. All real numbers. I'm going to put that as well. Now the y values, we look from the bottom up. This is going to have a y value along the y-axis everywhere, and then when it gets up here, it's going to switch this way. It's going to have a y coordinate anywhere on the y-axis. Again, that means every real y it's going to be in the range. So that's negative infinity to infinity. Okay? The good news is all linear functions are going to have those same domain and ranges. It's going to always be negative infinity to infinity. All right, now let's look at the circle. We already said this was not a function, but that doesn't mean it doesn't have a domain in the range. So let's look at the domain. We're going to scan our eyes from left to right. So this is left on the x-axis, and it appears to be -2. And this over here on the right is 2. So that means it has a coordinate on this graph everywhere from -2 all the way to 2. Because think of this point right here. Isn't that -1 and some value just below 2? So that would be hard bracket, because it includes -2, all the way to 2, and it includes it. Now for range, we scan our graph from the bottom up. So again, it starts at -2, and it goes all the way to 2. So that would be my range. I'm sorry, I forgot to put the domain range spot in there for you, that one. All right, this one, this is the graph of a parabola. It's the graph of the quadratic function y equals x squared, or like I said today, another way to write y is f of x equals x squared. All right, so if I want to find the domain, I scan the x-axis. Now I'm drawing these lines in to kind of help you, but if I scan the x-axis, and this is going on forever, it's going slowly out, okay? It's going on forever. It is going to have an x value every single place along the x-axis. So its domain would be all real numbers, so negative infinity to infinity. The range, though, is slightly different. So let me erase. The range, we scan from bottom to top. So the bottom value here is y, and it's rising up, meaning I'm going to have a y value everywhere above that point right there. That's called the vertex. And so my range as an inequality would be y is greater than or equal to 0. But in interval notation, we would write hard bracket 0 all the way to infinity. Because along the y-axis, positive infinity is up here and negative infinity is down here. All right, let's look at another one. This squiggle, okay? The domain. I look left to right along the x-axis, and it appears that this graph is going to have x values starting at -1 and going all the way to 1. So my domain would be -1, 1, and it's hard bracket because it actually hits the x coordinate of -1. The range, I scan up, down, and it has arrows at the end of the graph, meaning it's going to continue on. So it's going to squiggle through every single y value on the graph, which would mean negative infinity to infinity with parentheses. Again, we can also write that as all real numbers. All right, I want you to try this next one on your own and come back, okay? All right, so you pressed pause, you tried it. Hopefully you looked along this, and again, there should have been arrows at the end indicating it was going on forever. And so you hopefully saw that it was going to hit every single x along that x-axis. So the domain would have been negative infinity to infinity with parentheses. Again, for the range, I'm hoping that you really considered what I said. Go up, down. This graph doesn't start until I get right here along the y-axis, which is at 0, and then it goes on forever. It's going to have a y coordinate along the entire graph. So that would be y is greater than or equal to 0. That's inequality notation or interval notation, hard bracket 0 to infinity. All right, so I just want to see at the end of all of this if you can answer this now. Why is 2, 1, 3, 1 a function, but 2, 1, 2, 3 not a function? So I want you to answer that for yourself and bring it to class tomorrow. Guys, hopefully you enjoyed your lesson on domain and range, and have a great day.